Okay, just in case you weren't here today in class, a recap of our need to know. So frequency is defined as the number of waves per second. Period is defined as the time for just one wave. Amplitude is the maximum displacement from equilibrium, whether that's up, down, like compressed, rarefied, etc. And then wavelength, length of one wave. Frequency is little f, period is capital T, amplitude is A, capital A, and then wavelength is the lambda upside down y. These two are distances measured in m, period is a time measured in seconds, frequency is hertz, that's 1/seconds, because the relationship between frequency and period is that they're inverses of each other. So period is 1/frequency and vice versa. Wave speed is how fast energy is going through a medium, so that would be like a stadium wave. It's not how fast each individual person is standing up and down, it's how fast that energy, the wave, goes across the stadium. And then super important that you know V equals F wavelength. That is not on your equation sheet. Where it comes from is V equals T over T, distance being wavelength, time being the period, and then if you have wavelength over period, well, 1 over the period is just the frequency, so V equals frequency wavelength. So just something to memorize. Waves will transfer energy. They don't transfer actual matter from one side to the other. If you think about a stadium wave, the people aren't going across the stadium, it's just the energy is transferred between each of those people across the stadium. If you want more energy in a wave, you would increase the amplitude of the wave. Your wave speed is going to be constant in the same medium unless you change mediums, or if you make the medium different by changing this tension. So like for a string rope, if you increase the tension, that would increase the speed. Or if we're talking about like air, you could increase the temperature of the medium, and that would also change the wave speed in that medium. Or you can go to a totally different medium. Instead of being in air, going through water. That's a totally different speed. This is just a note to say if you have, let's say you have a rope and it turns into a thin string like this. If you send a wave, it will travel at a constant speed through this part of the rope. When it hits the string, it's obviously changing mediums. This will have a different wave speed. What stays the same when it enters a new medium is the frequencies. We haven't talked about that. That's just a fact you might need to know for AP. Average speed of a point, that's how fast a specific point is oscillating. So that would be in terms of the stadium wave. Wave speed is how fast the wave goes across the stadium. The average speed of point would be how fast an individual person is standing up and down or putting their arms up and down. This isn't something you fill in, it's just you need to know about wave interference. If you have two waves like this coming towards each other, they're going to overlap and make a bigger wave while they are overlapped. Constructive interference, if you have something like this coming towards something like this, that would be some sort of destructive interference. It's called superposition. That's when the waves are superimposed on one another. They overlap. They're interfering with one another. The superposition is when these two are on top of each other, they create this. Or whatever, if there's a flat line, depends on what the actual amplitudes are. Standing waves, so you get standing waves when you have an incident wave, an incoming wave, and a reflecting wave that interfere. So obviously the reflecting wave is the same wavelength, same frequency, period, etc. And if you have a confined region, that means that they're constantly sending new waves and constantly interacting with a reflected wave. And it's only very specific frequencies that will create standing waves. Or you can think about it as very specific wavelengths. Because you're not going to get, if you have a string, right, you can get a wave that looks like this. A standing wave that looks like this. Or like this. Or like this. What you will not get is a standing wave that looks like this. Where it's part of some random, if it's cut off right here. These two, for a string, it's going to be 2 fixed ends. You can get 1/4 of a wavelength. We did that in the lab where you had the closed end and then the open end, and it was a node and antinode like this. You can get 1/4 if they're one closed, one fixed. If it's both fixed or both open, they change by half wavelengths because one loop is half of a full wave. Your node are points of no displacement, and antinodes are points that oscillate with the most displacement. Two categories of waves. First is mechanical. That one needs a medium for it to transfer energy. Electromagnetic does not need a medium. That's going to be like light, X-rays, gamma rays, visible light, etc. The second category of waves is transverse and longitudinal. Transverse is when it oscillates perpendicular to the wave direction. So you could have the wave going this way, it would oscillate like this. If you have the wave going this way, then your oscillation is like this. Or in this case, you also could have like into the paper, out of paper. That's technically perpendicular to the right. And the wave doesn't have to always go to the right. If I have, I'll just do it up here. If you have the wave going like this, then oscillating side to side would be a transverse wave. Oscillating up and down would be a longitudinal wave. So don't say up and down means transverse and sideways is longitudinal. It's whether it's perpendicular or parallel. All right, sound. So sound is a longitudinal and a mechanical wave. Just you need to know. And then volume is determined by the amplitude of the wave, and sound or pitch is determined by the frequency of the sound wave. Doppler effect, we're not going to have to calculate, but you need to be able to tell whether it's like higher or lower frequency. If the source is moving towards the observer, or if the observer is moving towards the source, as long as they're going towards one another, then the waves are going to get squished together. It's a higher frequency, shorter period, shorter wavelength. And if the source or the observer is going away from one another, then the waves are going to end up spread out farther than normal, so you get a lower frequency, lower period, lower wavelength. If you have a slinky stretched out on the floor between two people to create a longitudinal wave. So if the slinky looks like this, then you would want to push it back and forth in this direction, which I said, like, if this is like the person right here, I said forward and backwards. Depends on how you drew your picture. If you're saying like the slinky is like this, then forward and backward. If like the person's holding it like this, forward and backward, it would actually not be longitudinal. It would be like whatever is in the same direction as the wave speed. But that's kind of random because I told you it's two people on the floor, so that actually didn't make sense. They would push it forward and backwards. To create a transverse wave, you can do side to side, like left, right. Or you also can do up and down. So if this is, again, your wave, you can literally have it going up and down like this, or you can have it going side to side like that. If you can imagine the 3D version of that, side to side. How would you create a wave with more energy? You would send more amplitude. So you would have to put more energy into it. Like you would be doing more work to send it the wave with more amplitude, because amplitude has to do with the energy has to do with the amplitude. What do you do to create a wave with a shorter wavelength? Well, you know that the speed of the wave is going to be the same. So if you want a shorter wavelength, that just means a higher frequency. Because your V equals F wavelength, you would increase this to decrease this, because this is going to be constant. So we would just say increase the frequency. You would send more waves per second. E, what would you do to increase the average speed of a point? So if this is your slinky, how fast the wave is moving is how fast that compression or cross takes to go through the slinky. How fast an individual point is moving depends on how far up and down it's going. So what we could do is we could increase the amplitude. And it also depends on not just how far, but like how long does it take to go up and down, etc. So you could also increase the frequency, which is the same as decreasing the period. So if you think about like the stadium wave, right, you can have a big amplitude, but if you take a really long time to like go up and sit down, then you're not actually moving that fast. Whereas you could stand up and sit down really fast, frequently, with more frequency, you're going faster. That point, not the speed, not the wave. What would you do to create a wave with faster speed? So you're going to have to change the medium somehow. For a slinky, you could just increase the tension. That would increase the wave speed. All right, number 2, we've got 2 wave pulses on a string traveling towards one another, t equals 0. This is the picture at t equals 0. At t equals 1, the pulses completely overlap. So t equals 1, A, B, and C, A, B, C, they're completely overlapped. So you have this one plus this one, which would then just make a big one, and the rest would be flat. And then at T equals 2, now they've passed each other. So now this guy would be on the other side, and A would be like over here. So A, B, C. I guess A and B wouldn't be over here, but this pulse would now be at A, and this pulse would now be at C. So this is the bigger one right here. So then you're filling in at T equals 1. At B, this is 0 and 0 because they've completely overlapped. So the two amplitudes would add together to get 8 meters. And then at 2, now they've passed each other. They're not interfering. It's just that this one is over here and they've switched. So this would be 5 and this would be 3. So A. Number 3, a transverse wave is traveling on a string. This shows the position as a function of time for a point on the string. So this is saying this one point is going up, and then it's going down, and then it's going up, and then it's going down as this amount of time has passed. Now we're going to double the frequency of the wave, and we want to know what the average speed of that point is. So you can find average speed of the point right now. You can say, okay, it goes up 10, down 10, that does 20 in point 2. Or you can say it goes 10 in point 1. Or you can say it goes 40 in point 4. It doesn't matter because the average speed, once you have it, is going to be constant through it.